Welcome to a volume by shells example in Y. So again, shells in Y, we're looking about rotation about the x-axis. So for this example, let's find the volume of the rotational solid formed by rotating the below shaded region about the x-axis. The region we are working with here is the region that is below y equals natural log of x and above the x-axis. And the region stops at x equals e squared. So of course, natural log hits the x-axis at 1. So we're essentially running from x equals 1 to e squared, looking above the x-axis below natural log of x. So this time around, we are rotating about the x-axis. If we draw this picture, we essentially are looking at a solid bowl, basically, right? So we could do with this with discs, and the discs would have radius natural log x. Again, we would have a natural log squared. So note, if we used discs, then our radius would be natural log of x. And so we would have to integrate natural log of x squared dx involved. On the other hand, if we use shells, I'm again just going to draw them here. So our shells this time, we pick a horizontal cross section of our region. We rotate that around our x-axis. And then that will have thickness dy. So for our shells, essentially we have thickness equal to dy. For our radius, we will need to rewrite our radius as an r of y. So we have our radius runs from the x-axis to natural log of x. Oh, sorry, our radius is just r of y equals, our radius runs from the x-axis to our y value. So the radius runs from the x-axis to our y value. And so we just have our r of y is just y minus 0, otherwise known as y. Again, this is because we're running from the x-axis. So we're running from a y value of 0 up to y. For our height, if we look at our cross sections, our height is running from x up to e squared. So the height runs from x to e squared. So our x to figure out x in terms of y, we have y was equal to natural log of x. So that means that x is simply e to the y. And so we have that our h of y is e squared minus e to the y. So putting all this together, we have that our dv is equal to, we do circumference, 2 pi r of y times the height h of y times our thickness dy. So we are looking at 2 pi times y times e squared minus e to the y dy. That means putting this all together for our volume, we have to figure out our bounds. So x is between 1 and e squared. Y is simply the natural log of x. So we have y is between the natural log of 1 and the natural log of e squared, otherwise known as 0 and 2. So our volume will be equal to, we have the definite integral from 0 to 2 of 2 pi times, we have our radius, so 2 pi times r of y, we can skip that, 2 pi times y times e squared minus e to the y dy. So we are looking at 2 pi times the definite integral from 0 to 2 of e squared y minus y e to the y dy. E squared y we can easily integrate. Minus y e to the y. If we set our u to be negative y, our dv to be e to the y, then we'll go to negative 1 and 0. E to the y just goes e to the y and then e to the y. We take positive product of the first, negative product of the second, add the integral. We wind up getting, we are looking at 2 pi times e squared y would go to e squared over 2 times y. Then we will have minus y e to the y plus e to the y evaluated at 0 and 2. So again, that minus y e to the y plus e to the y is my integration by parts. That e squared over y goes to, sorry, that should be an e squared over 2y squared. I lost my exponent on the y. We're evaluating at 0 and 2. So we are looking at 2 pi times e squared over 2 times 2 squared minus 2 times e squared plus e squared. Then from that we are subtracting off, and e squared over 2 times 0 squared minus a 0 plus e to the 0th. Again, all of that is multiplied by the 2 pi out front. So we are looking at 2 pi times, we'd have a 2e squared minus 2e squared cancels out. We're just left with e squared. And then we are subtracting off 1. So we have that our volume is 2 pi times e squared minus 1. So again, this is just another route we can take for finding volume. We don't have to worry about looking at natural log of x squared in our integral. And instead, we can work with an easy y e to the y and just a constant times y. Right, in the next video, we will look at rotating around an alternative axis. So just some horizontal or vertical line.